properties, states, path, process, cycle, and then talked about the zeros law of the thermodynamics. I think this one was the last topic that we were talking about. Now I will continue from the zeros. Now I will continue from the zeroth law of thermodynamics, and then move on to the next chapter. So we have said that zeroth law of thermodynamics states that if A is in thermal equilibrium with B, similarly A is in thermal equilibrium with C, and then B and the C are in the thermal equilibrium with each other according to the zeroth law of thermodynamics. Similarly, so we have built an analogy between the zeroth law of thermodynamics and the real life, and we have said that in real life, if A has some same richness as B, and if A has same richness as C, if they have the same richness, then according to some law, so it is not the zeroth law as in thermodynamics, but it is some law that it says that there is the same richness between B and the C, according to the first law of, or zeroth law, or the whatever law you know. And the combination that holds for all of these cases is the money. The money is the property that holds for all of these cases. And in this case, the property that holds for all of these cases is temperature. And we have also said that when the temperature, the people started to study thermodynamics, they didn't have any knowledge about molecular interactions. They didn't know any molecular view, because thermodynamics started to emerge as a science from 17th century. And for example, 18th century, the people didn't even believe that molecular views are right till the mid of the 19th century. Okay? So from these dates, from 1850s, we can say that the people started to study statistical thermodynamics, and therefore the classical and statistical thermodynamics, so they give the same result, but the definitions are different. For example, in statistical thermodynamics, you can say that temperature is the kinetic energy of molecules. But in classical thermodynamics, the thermodynamics that we are studying in mechanical engineering, which is the classical historical thermodynamics, we can say, in this case, we didn't have any molecular view, and therefore the temperature definition was very different from the statistical one. And that is the definition that we know here. And we have also said that the thermodynamic scales, we use Kelvin scale instead of the degree Celsius scale, because this one is the absolute temperature scale, and this one is the relative. Okay. And this one was the results of the previous lecture. And also we have said the Kelvin temperature starts from the absolute 0. And in that case, the degree Celsius is negative 7 to 3.15 degrees Celsius. That is the difference between Kelvin and the Celsius scale. If it is division, so if it is division, or if it is the multiplication, then you have to use the Kelvin scale. But if it is addition, if you add some stuff in degree Celsius, then you should use the subtraction. If it is subtraction, then you should use the Celsius scale. So the Kelvin scale and the Celsius scale gives the same result for subtraction. Okay, this both gives the same result. But for the multiplication and the division, you have to be careful. You have to use the Kelvin scale. Otherwise, you will get the wrong results, which we have discussed in the last lecture. Now we are going to move the last parts of our chapter 1, which is the temperature measuring devices. We will have also the lab session for this one. So the temperature measuring devices can be divided into 4 groups. We have temperature measuring devices, or the thermometers that we know as a famous name. So these are also called the thermometers. Okay, they are grouped into, you can classify them into 4 groups. One is the using the thermal expansion of the materials or substances. I will talk about each of them separately. And some of them uses electrical resistance of the materials, because at the end for all of these classifications, you need some property some property sensitive to temperature. Okay, there should be some property that is sensitive to temperature, and that sensitiveness will give you the amount of the temperature that is present. Okay, for example, your skin. When you touch something and you say that it is hot, and if it is cold, you know it is cold. Okay, because your skin is sensitive to the temperature. Similarly here, for any device and for any property that you are using to measure temperature, it should be sensitive to temperature. But the being sensitive is not the only property that we are looking for. We are also looking for the linearship, so the relationship between the sensitiveness, say that this is sensitiveness, and the temperature. It is better, but not always possible. It is better to have a relationship between sensitiveness and the temperature to be linear. Say that this one, or this one, or this one. Because the linear relationship, firstly, it is easy. And the second, it is more accurate. And the third one, it is best for sensors. If you have sensor, linear one is better to implement. Okay, there are sensors that working on nonlinear relationship like exponential or parabolic, but due to the easiness of the linear relationship, we are mostly looking for the sensitiveness and the temperature relationship that is linear. And in most of these cases, you will see that it is linear. And the first case uses the thermal expansion property of the materials, which is sensitive to temperature. And the second one uses the electrical resistance of the materials, which is also sensitive to temperature, like conductors, semiconductors. They have the electrical resistance sensitive to temperature. This is the second property that we are looking for. And the third property that we are looking for, it is also called the thermoelectric or the thermocouple. This is also very famous. So this one here, you have the voltage. You will see it in some minutes. Some metals or the materials have sensitiveness to temperature, but the result is voltage. So you will have the production of the voltage. And some are radiative thermometers, which has the optical pyrometer and the infrared thermometer. Due to COVID-19, you will see this one more often in the entrance of supermarkets or the university. This one has become widespread, but this is new technology. And it uses the radiation properties of the materials we will talk about in minutes. And also there is optical pyrometer. This is again uses the radiation properties of the materials. Okay, these are different classifications of the temperature measuring devices. In our laboratory, we don't have this last kind of the device, radiative thermometers. Okay, but these three are in our laboratories, and we will do experiments for each of it. Good. First, the thermal expansion.
Optical pyrometer var idi. Optical pyrometer.
Yes.
Optical pyrometer has tikimi.
So we will have the presentation for each of it. Okay, you will have the presentation. I will talk about each of it. The first one and the second one. So in sequence, I will talk about each of it. Okay, so first, the thermal expansion. I will start from the first one. Thermal expansion can be the easiest one, which is very famous. Even at your home, you have the mercury thermometer. Here, the volume change of the material is sensitive to temperature, but that volume change of the material or substance is linearly proportional to temperature. That volume change of the material or substance is measured by this coefficient, alpha. So I will write the coefficient, but it is not so difficult as seems is in equation, dt by the pressure. Here you have the volume, the partial derivative of volume with respect to temperature, but P here means that it is at constant temperature, at constant pressure. Okay. So what will I do now is that, so if I write this quantity and approximate this one as linear, okay. If it is linear, the derivative can be approximated as the division of the two deltas, and I can write this one as 1 by delta V by delta T. Okay, this V is initial V, the initial volume. Say that this is the initial volume of the mercury. And this quantity, I can one more step and simplify it. I can write it as initial divided by the delta T. The alpha says that how sensitive the material is. You see here, I am dividing the volume change due to temperature change. This volume here changed due to temperature. The reason is temperature change. You have 5 degrees Celsius, for example, temperature change. As a result of it, the mercury's volume change, say that 3 milliliters. Okay, so but you are measuring this volume change with respect to its initial volume. Okay, so how sensitive it is to its initial volume in response to temperature change. Say that it is not very sensitive. This is its initial volume, and say that this initial volume change this amount. See, there is change here. You can see there is change, but not too sensitive with respect to its initial volume. The initial volume is the most important one. But if I have a initial volume something like this one, and it has changed to a proper volume something like this one, volume final, and this one is the volume initial. You can see now the change in volume. This one has more sensitivity than this one. Okay, therefore the quantity here, delta V by V initial, you can call it also the sensitivity. Okay, so you can call it also as sensitivity. It measures how sensitive the material is to temperature change in response to temperature change. And mercury is good, so therefore we are using mercury, and they are also using the alcohol. Okay, so they are sensitive to temperature, and this is one property. And another property for these temperature measuring devices is that you have to have a material substance, so it doesn't freeze at 0 degrees Celsius and it doesn't boil at 100 degrees Celsius. So freeze, not freeze, and not boil. Okay. It is true that we don't have 100 degrees Celsius environment most of the time. Therefore, this part is not often used, but this part is very important. At least it shouldn't boil till 80 degrees Celsius. Okay, it shouldn't boil, and it shouldn't freeze at 0 degrees Celsius. This is another property that we want from these substances. Okay, this is very important. Otherwise, this one, the material substance that you use, will fail for temperature measurement. Okay, good. And here we have this is the first one, the mercury, famous one. And there is also bimetallic temperature sensors. So for bimetallic temperature sensors, you have two metals on top of each other. So we have copper or brass, and underneath it you have the invar. Invar is it is an alloy of nickel and iron. Okay, it is an alloy of nickel and iron. So the two metals are on top of each other. When you are heating this part, say that you are heating, and the copper has more sensitivity to temperature, similar to mercury. But for metals, instead of talking about volume, and we are talking about the linear change. Say that this is copper, initial length. Okay. And when you start to heat copper, it gets something like this one, and this amount of delta L. So for metals, instead of talking about this quantity, you can say that alpha is delta L by L initial divided by delta T. Okay, you see the volume, and here you talk about the length. Okay, so this is the for metals, but the general definition is this one. Okay, you see, general definition is this one. But for simplification, you can use the length of the metals. And when you heat the metal from underneath, and you will have a change in the length of the copper or brass. It can be any different material, aluminum, etc. But the problem here is that you should use another metal here. So one metal is not enough. Why the one more metal is required? Because when the copper deforms, let's say it gets something like this one, a shape. Okay, this is after heating. Okay, now it becomes cold. It becomes cold now. What will happen to this copper? And it will change its shape, deform. Okay, it will deform when it cools, but we don't want it. We want the metal to keep its shape. Therefore, we put another metal underneath it and glue it, stick it to each other. Okay, these are together. And this second metal, invar, which is the alloy of nickel and the iron, is not sensitive to delta T. Okay, so it means that alpha is equal to delta L by L divided by delta T. So if you change this delta T for 20 degrees Celsius, let's say, and this delta L by delta L is very small, doesn't change too much. Okay. Therefore, since this one, the bottom one, keeps its shape, so this one keeps its shape, okay, and it doesn't let the copper deform. So deformation doesn't always happen when you cool it. It can also happen when you heat it. Say that this is the copper initial shape, and when you heat it, it can get something like this one. Okay. It doesn't mean that the deformation happens during cooling process. In heating process also, you can have the deformation. Okay. Therefore, it is very important to have another material like this one to prevent the deformation. So this, the combination, it's also called the bimetallic. Bimetallic, you can say bimetallic because there are two metals here. And you can see this combination in kettle. If you have kettle at your home, after some degrees, the kettle stops. Okay, the electricity circuit breaks. Why? Because you have this combination inside your kettle. When it is heated to 100 degrees Celsius, and this one deforms, or this one the elongates, and therefore the contact breaks, and you have the electricity cut off. Okay? That is the reason. And it is used not in kettle. In most of the places, you have the bimetallic sensors because it is mechanical. It has more durability than other sensors. Therefore, we use bimetallic sensors for most circuit breaker. For more circuit breaker, we are using this bimetallic sensor. But how do we employ it for the temperature measuring device? To employ it for temperature measuring device, instead of using this one as a plate, we use it as a spiral. Okay. When do we use it as a spiral? Again, you have this combination, the copper or brass, on top of nickel iron alloy. Okay, they are on top of each other. And when you have a temperature change here, let's say that this is T hot, this temperature change causes this spiral element to elongate in one direction. Okay, it gets longer. As it gets longer, it rotates. Okay, it rotates. And here you have the gear combination. You have the gears. Yeah, and this gear combination allows to change this linear motion into rotary motion here. Okay. You have the linear motion here inside this sensor, and this gear combination allows us to convert this linear motion to rotary motion of this arm. And due to this arm, you can find the temperature of the environment. But the most important thing here is not the first step is the calibration. You should calibrate all of these devices. Okay. And then after calibration, you can find the temperature of the environment. Calibration means that this one, for example, the calibration depends on your purpose, however you want. So at 0 degrees Celsius, the sensor, the arm is here. Arm is here. And then you calibrate one more step because 2 steps is required for linear calibration. For 5 degrees Celsius, you calibrate it one more time. Okay. And then the steps will be okay. It will work for all of these steps. Similarly here, you should calibrate it. So if you don't calibrate it, you cannot see any values here. You should calibrate. For example, it doesn't mean that when you have the initial volume, it should show the 0 degrees Celsius. It depends on you. Okay, it depends on you. You should select such volume that you can select such volume that it shows 20 degrees Celsius at its beginning. Okay. Depends on your calibration, but it should be correct value. Okay, at 0 degrees Celsius means that environment is at 0 degrees Celsius. Good. And here are the table of the alpha, the thermal expansion coefficient of different metals. Aluminium has a 9, 10 to the negative 6. You can see the smallness of the value. And what it is, it shows the change of, so this table shows change of volume with respect to initial volume per 1 degree Celsius. So if I heat aluminium 1 degree Celsius, the change with respect to initial volume will be 9 times 10 to the negative 6. If you convert that quantity into the percentage quantity, it means that for 1 degree Celsius, aluminium change its size 10 to the negative 4%, which is del V by V initial. For copper, it is 9.4, 10 to the negative 4%. So you can see this change, how small, you can see it is very, very small. Very, very small means you can have errors in measurement. So accuracy, precision is where comes into picture. Brass is 11, 10 to the negative 6, and the invar, which is the, I've said it is not too sensitive, you can see 1.7, 10 to the negative 8. You see, it is 100 times less sensitive. 100 times. It actually is not 100 times, it is 800 times. 800 times less sensitive than the other ones. Therefore, invar is used for preventing the deformation. But this is the first part. And the gas thermal expansion, it is too early to talk about this one because it is all about ideal gases. We will talk about this one in after 2 chapters. But it is a very similar concept here. So you have the ideal gas inside the tube here. So instead of this spiral, you have ideal gas here. Ideal gas volume is sensitive to temperature. Therefore, when you change the temperature, you change the volume of the ideal gas. I can summarize it here, but it is not too important in all of the concepts of the ideal gas because it will be after 2 chapters. So here you have the ideal gas. So when I heat this one, its volume changes. Volume goes up, let's say, when you increase the temperature. And when the volume goes up, it changes its pressure. Okay? And therefore, as a final result, you have the pressure change, delta P. But the reason is delta T. You can see the pressure change, but the delta T is the reason. There are intermediate steps, which is the volume change, but the final response is delta P. So you have the relationship between delta T and the delta P, and therefore you can find what is the temperature inside the room by knowing delta P. Okay? So you know pressure, and from that pressure you infer the value of the temperature of the room. Okay? That is for ideal gases. Now comes the second classification, which is using the electrical resistance of the metals. Again, you have the similar relationship with the first one. Here you have the electrical resistance instead of the temperature, instead of the volume. So in the previous case, we were looking for the change of volume with respect to initial volume as a response to temperature change. Now you are looking for change of the resistance with respect to initial resistance as a response to temperature change. You see similarity? And also in the same way, we are looking for the methods or the materials that have the linear relationship. So in the first case, we have said the change of volume, this one with respect to temperature should be linear. So if I write this one as delta V by V initial should be K into delta T. So linear change. If you remember, F is Kx. Okay. X is this one. F is this one, and the K is the constant. In spring, it is stiffness. Okay. And here it is some temperature coefficient. Temperature coefficient. You see the similarity is very important. But it is not always that you will have a linear relationship. Sometimes you can have parabolic relationship, even exponential relationship is possible, but the linear one is the desired one. If you have the linear relationship, then you are lucky. If you don't have the linear relationship, then you should use some linearization. But now let's go back to here. So for the electrical resistance, we have different methods and the semiconductors. For the metals, the famous one is platinum 100, PT100. It is also called PT100. What is PT100? PT is the name of the metal, which is platinum. 100 means that this one has, PT has 100 ohms at 0 degrees Celsius. When there is 0 degrees Celsius, this PT metal, say that this is a rod of metal. This is rod of platinum metal. Platinum metal at 100 degrees Celsius has 100 ohm. So 0 degrees Celsius, but 100 ohms of resistance. Now I increase the temperature. Say that I'm trying to measure the temperature of the room. So I put the PT rod, the room which has a temperature of the 20 degrees Celsius. But I know from experiment that you can see PT1 here. PT are the black ones. You can see PT here. If I use different color here, so this is the PT. You can see the linearity. So you can see the linearity in most of the temperature sensors, most of electronic components. Okay, even laptops. So you are using PT100, not so large, or small PT100. Okay, most of the sensors, if you are curious about the type of the sensor, you can look at it. It will be either PT100 or it will be the thermocouple that we'll talk about in next slide. Okay, good. This is the PT100, and this is the resistance of the PT100 in ohms. You can see the ohm, and this is the temperature change. I increase at 0 degrees Celsius, it will have the 100 ohms. It's 100. Approximately 100 at the 200. So sorry, it is not at 0 degrees Celsius. That is the error that I am having. Good. 0. It is not at 0. It should be at 25. 25. At 25 degrees Celsius, it has the 100 ohms. Okay. So that is the reason that I have error here. It is 25 degrees Celsius. That's 100 ohms. Good. So I'm trying to measure the temperature of the room where it is 20 degrees Celsius. And I know that it is linear. If I know this linear function, which is kt plus b, k is the coefficient, b is the intercept that you will have from the y-axis. And then from this one, I can find the resistance. Okay. Or I can do the opposite case. I measure the resistance of PT100, and then I find the temperature of the room. How do I measure the temperature of the resistance of PT100? So PT100 doesn't measure the temperature alone. It is a part of the circuit. So here you have the PT100. It is inside the circuit. Okay. So say that PT100 is here. You are trying to measure the temperature of the room. So inside the room, the resistance of the PT100 will change. As its resistance changes, the current that flows through PT100 will change. So therefore, from the drop of the voltage, you can find what is the temperature inside the room. Okay? It is for PT100. For nickel, you can see the nickel is not good because it is not linear. You can see this one is not linear. It is not good, but some time, we can use the nickel. Where do we use it? We use for this small range. And see, for this small range, this one is linear. You see, the linearity is the property that we are always looking for. For copper, the green one, you can see it is also linear, similar to platinum. But we don't use copper, we use platinum because it is more sensitive than the copper. Good. And also, one more thing here is that we have also, these are metals. We are using metals for the temperature measurement. And you should notice here that if I increase the temperature, the resistance increases. If I increase the temperature, resistance increases for metals. Now, sometimes we also use the semiconductors. You can see here on the right axis of my graph, I have the semiconductor. And the semiconductor is at this one. This is the semiconductor. Okay. But you see here, as I increase the temperature, this is in logarithmic scale, okay, logarithmic scale, because the values are very large. Therefore, I should use the log scale to see it clearly. For the for the semiconductor, as I increase the temperature, its resistance drops. See, resistance drops. Therefore, it is exponential, but exponential, e to the power of something. Okay, it is exponential drop in temperature. But we are also using for semiconductors. They have semiconductors. Why we are using this is the most sensitive. But the bad side is that it is not good for all of the temperature measuring range because it is exponential here. Okay. The bad thing about exponential functions is that if you know the exponential functions, after some range, you see you have the change of property, you have the change of temperature, but this one is not sensitive. You see, it gets asymptotic to the line here. However, you increase the temperature, the property here doesn't change. That is the bad side of the exponential functions for temperature measurement. And therefore, semiconductors are not used for all of this range, but they are used in some range around here. You see the linearity again. Okay. But so if you try to use the linear part of the semiconductor always, you can have some errors because it is not perfectly linear. It is approximately linear. Therefore, you can have the accurate problem here. Okay. So to resolve the accuracy problem, you have to use higher order approximations. And the higher order approximations means that you should not use the linear approximation. If you don't use the linear approximation, now comes the complexity. Okay. There is no free lunch. If you want to get rid of one part, you have to be ready for another difficult part. Good. So far, so good. This is for the temperature measuring properties of the metals. And here we are using the sensitivity of the resistance. As I said, here the volume is sensitive. Volume change is sensitive to temperature. Here, resistance change is sensitive to temperature. Good. Now comes okay, one thing I have forgotten here is that, so melting point of the metals. Melting point of metals. For example, copper melts at around 1000 degrees Celsius. Okay. So it means that you cannot use the copper in that the resistance thermometer at that temperature. Okay. Therefore, you should be careful about the application temperature of the sensors. But as I said, the PT100 is very famous, and semiconductors are famous in some electronic components, but the PT100 is the inevitable part of the industry. Okay. In most of the sensors, if you look at it, it will be PT100. Even if it is not PT100, it will be thermocouple. If it is not the thermocouple, it will be semiconductor. Okay. The other ones are not used too often. Good. Now comes another. So we have talked about this one. We have talked about this one. Now comes the thermoelectric or the thermocouple. This the second very famous one. It is used in the fluid flow. We use the thermocouple. In industry, we have to use the thermocouple. Okay, so that is That is the one of the most famous temperature measuring devices. So how it works? For the thermocouple, we are using the Seebeck effect, which is from 1821. So Seebeck has found this effect. So how did he found that effect? So you have one metal B, you have one metal A. So it can be any combination of metals. Here you have the junction of the metals. So junction means that I have tied this metal with this one. So wound up. So this metal has a junction with the metal B here. And also the same junction around here. This metal junction is at T reference. T reference means that I know the temperature here, which is 0 degrees Celsius. And the junction B is at some unknown temperature that I'm trying to measure. The funny thing about the metal combinations is that if you heat one of these junctions, so say that there is T1 and there is T2 and there is difference of temperature, which is delta T. If you heat and you have the delta T between these junctions, and you will have voltage produced. Okay. So one more time, I have metal A and I have metal B. This is Seebeck effect. I think you should know it from physics course. So then you have two junctions here between two metals, metal A and the metal B. It can be iron, copper, or it can be, here combinations I will show you. So I am heating one part, let's say that this part, and this part is not heated. This is at, for example, room temperature, 25 degrees Celsius. Okay. As I heat this part, there will be voltage, electron flow. Electron will flow due to heating effect, because heating means, so you have the higher, so you have moving free electrons. So these electrons move. Okay. It moves from one side to another side. And as the free electrons move, you will have the voltage difference between these two junctions, or EMF. Okay. So another thing here is that if you remember from these coefficients, so similarly here, the voltage change with respect to the initial voltage, this one is voltage, not volume, this one is also voltage, is again proportional to the temperature change in a linear manner. Okay. The temperature change causes voltage change, more temperature change causes more voltage change, but in a linear manner. Okay. There are different combinations of the metals, and due to different combinations of the metals, we have different type of the thermocouples. We have the J thermocouple, which uses iron and constantan. Okay. And it's also alloy of 45% of nickel and 55% of the copper. It's an alloy. So you say that metal A is iron and the metal B is the constantan. Okay. And these metal combinations gives you the voltage difference between these two points, between the parts, and then from that voltage difference, you know the temperature of the environment. As again, I said, you know it because you have done experiments with this thermocouple, and you know that it is linearly changing with respect to temperature. Linearity, and linearity. These are the final words of the inventors. Okay, good. So you have the iron, you have the constantan, and this is the type of the thermocouple. You have copper plus constantan. Here, instead of iron, you use the copper and the constantan, and this is T-type thermocouple. You have the K-type. This one is the most famous, most common. In our laboratory, we have K-type thermocouple and also J-type, if I remember correctly. We have both of these, J and the K-type. Here you are using the chromel, which is the 10% chromium and the 19% nickel, and the alumel, which is the 95% nickel, 2% aluminium, 2% manganese, and 1% silicon. Okay, so this is an alloy, okay, the alloy of different metals. So we are using these combinations for the temperature measurement. And the last type is the E-type, which is called the chromel and constantan. Chromel is this one, constantan is this one. And so why do we use different metals, different combinations? This is the first question. And the first answer to this question is that the application areas are different. Okay? Because the J thermocouple, it's best to use in non-oxidizing environment. If it is oxidizing environment, then you will have problem with this J thermocouple. Okay? Or the reducing and the vacuum environments, it is best to use T-type thermocouple. Okay? And if it is high temperature values, if you are looking for high temperature, use this one, K-type thermocouple. And you can also see the second reason, there is a limiting temperature here. Okay, 760 degrees Celsius. It is better to use under that temperature. Why? Because if you increase the temperature more than that one, you will have two problems. One is linearity is off. This is the bad side, and the two is melting problem. Maybe, okay, maybe. I don't say it can be. So this is one example, but maybe you have some melting problem. Okay? But the main issue here is that the linearity. If you go more than 760 degrees, you will lose the linearity, and then you will have the problem. Now for high temperatures, you can use K-type thermocouple, again limiting temperature. And the E-type is the highest sensitive among these. So this is the last one, E. So sensitivity means sensitivity. You have two definitions for sensitivity. One is when we say sensitivity, so you have the temperature change, okay, and you have the volume change, for example, or you have the resistance change, or you have the voltage change. Okay. This is the first part that we want from sensors. There should be response. Second thing, as I said, always we want it. And the last thing that we want from sensors is that time constant. Okay, time constant of the sensors is also important. What I mean by time constant, say that you are touching a hot surface. When you touch the hot surface, you just at that instant, take your hand off, because the time response, time constant of your body is very high. Okay, actually it is very low. Okay, low. Time constant of your body is very low. The low time constant is very important. But say that you have a sensor, take your body. Say that you are touching some hot surface and your time constant is not good, is not optimum. What will happen is that when you touch the body, okay, you don't feel the hotness, and after some time you feel the hotness, but it is too late because you have the burnout problem. Your skin has burned. That is the problem. Similarly for sensors, and I want to measure the temperature of the room. I put the sensor in the room. I'm trying to measure the temperature, but you wait for a long time and say that after 1 hour, you see the temperature of the room, which is 20 degrees Celsius. But during that 1 hour, so maybe that the room temperature increased to 25 degrees Celsius. You see, here you are lagging. The sensor lags 1 hour before the real temperature, because it shows the value after 1 hour. The room temperature is 20 degrees Celsius, but its time constant is very high. You wait for 1 hour. After 1 hour, it shows the value which is 20. Lazy, let's say, lazy. And since the sensor is lazy, it shows the values 1 hour late. It lags. We call it lag. Okay? And the real temperature is 25, but it shows 20. This is another important thing that we want from the sensors. Good. And now comes the essential part of the sensors, which is the linearity. You can see the VE means the E-type thermocouple, and the V means voltage change, delta V. Okay. You can see here at 0, all of them shows 0 voltage. Okay. Say that this one is 20 and this one is 20. There is no temperature change. See, 0 and the 0 voltage. And I increase the 200 volts. I have here, let's say 15, you see, you need millivolts. 15 millivolts. So temperature here it is 220 instead of 20. And here you have created 118 volts. Okay? And so most of them are linear after 0 degrees Celsius. And you see some ending problem here. Which one? See? So one is low. You can notice it here. T-type thermocouple. Okay, T. T has stopped to show the value 20. And then we have the VJ, And you can notice the VE here. It goes very fast because it is high sensitive. Okay? Because it is very sensitive to value. If it is 60, it changed from 200 to 60. It has changed. Let me erase all of these one and to show it clearly. If you move from 200, 400 to 600, you will have this amount of millivolt change. You see, but for other thermocouples, say that for the K thermocouple, which is this one, you go from 400 to 600, you have this amount of change. You have this amount of change. This one is more than that one. Therefore, sensitivity is also important for the temperature sensors. This is the last. No, this is the thermocouple one. Now comes the last one, which is the radiative properties of the metals. Now I will talk about this one. So we have here two parts, which is the optical part, which is very important part. So how do we measure the temperature of the? So one more thing here is that these are the indirect contact. So here you don't have any contact. It's indirect. Okay, there is no any contact. It is indirect. So somebody holds this infrared thermometer from a distance to your forehead or to your hand, and he knows the temperature of your body because there is no contact. And how do we measure it? So I have here a simple example, but it is a more advanced topic for heat transfer, which will be second semester. So the metals, so the best thing to visualize it is the stove. A stove at your home. So when it has low temperature, it is black. Okay. When you increase the temperature, it becomes like that. I don't know, temperature red. Okay. High temperature and low temperature. Okay. At low temperature, it is black. As you increase the temperature, it becomes red. Okay. So it means that the temperature of the bodies has color to temperature relationship. Okay. It is not the color that is more important. It is also the lambda. Okay. Because you can see here, the lambdas of the materials is sensitive to their radiation emissivity. They are emitting. So they are the emitting means that this surface emits radiation, this surface emits radiation, gives off energy, okay, gives off energy. That energy, so this energy that is given off from surface gives off energy. That energy is proportional to the lambda, or the temperature, okay? And that was also proportional to lambda. So if I measure the lambda, I can know the temperature of the surface. That is how the infrared thermometers work, because they are measuring the frequency emitted from the surface. And then from that frequency, they're finding the temperature of the surface. Very good. But for optical thermometers, this one, pyrometer, this is industry, and it is more advanced. In this case, you are not using the lambda emitted from the surface, but you are using the color of the surface, okay? Say that color of the surface is red, and you have a lens. This is the lens inside your temperature measuring device, and what you are trying to do is that match the color of the lens with the color of the object. Okay. If the object is red, you are trying to match the color inside. Let me talk about this one separately here. So optical one, and finish the temperature measuring thermometers. So you have a metal here, hot metal, and it is color of red. And you have a camera here, and there is a lens. Okay. From that lens, you are looking at that hot red object. Okay. And what you are doing here is that you have a spiral here. So electricity or current. Okay. So to know the temperature of the surface, you are here you are increasing the electricity. More current flows till the electricity current gives the same color as this one. Okay. If it gives the same color as this one, okay, and here you know the power of the electricity power, and that power is proportional to the temperature of the surface. Okay? Because these relations are known. These are black body relations. It will be for the second semester. Okay, but for the simple cases now, so from high school, you notice sigma to the power of 4, Stefan-Boltzmann relationship. You know the power that is proportional to T to the power of 4 for black bodies, simple bodies, and then you can find the temperature of the surface. That is the optical pyrometer, and it is used in industry. But the infrared thermometers, they are using the lambda. They are using the lambda that is sent from the surface. Good. So we'll have the lab session for this one. We will have the lab session for this one. We will have the lab session for this one. But for the last one, we don't have any lab session. Okay? We will do lab experiments for all of these and measure the temperature of the different cases with different thermometers. You will use mercury. You will use bimetallic. You will use gas. So you will use conductors, semiconductors, thermocouple. Okay, you will use all of it, and you will find the temperature of the surface. Very good. Now we have finished the temperature measuring devices part, and now comes the pressure, which is the last topic of this first chapter. Yeah. What is pressure? So again, we will not talk about the molecular interactions because it is not so important. So, but if you go to molecular interactions, pressure is that the molecules are colliding with the wall here. This is say that the vessel. Okay. There are inside it, there are lots of molecules. These molecules are hitting the surface here. They are hitting it, and they have some momentum of mv, and that mv momentum is transferred into the wall, and those transferred momentums emerge as pressure. Okay. So they are hitting with the wall, So as a result of these hittings, the collisions with the wall will have the pressure manifestation. Good. And but for the experimental, for the classical thermodynamics, this one is not important. For classical thermodynamics, I have a sensor here, okay, and this sensor shows the value of the P pressure. That's all. Okay. It is experimental for classical thermodynamics. There is no molecular view. Therefore, here what I feel, that is all. What I see, that is all for classical thermodynamics. Inside the material, yes, there are molecules, there are quanta, something else. But for the macroscopic view, I have a sensor, I know the temperature. That is all what we want from classical thermodynamics. And we divide the pressure into 3 different parts. One is the absolute pressure. It is measured from 0 Pascal, reference is 0. Okay. One is the vacuum pressure, which is between 1 atmospheric pressure and the 0 Pascal. And the one is the gauge pressure, which is the devices. Okay. Devices use gauge pressure. If you have car, for example, I can give you example for gauge pressure, because if you have car, the car tire pressure. Okay. So it can be in SI unit, or it can be non-SI unit. It can be PSI, or it can be the kilopascals or bar. So whatever this pressure that is inside your car, it is not the absolute pressure, it is relative pressure with respect to ATM. Say that this is 5 bar. Okay. If it is 5 bar pressure inside your car, say that this one is, I don't know, 1470, 80 PSI. With this amount of pressure inside your car tire, doesn't mean that there is 5 bars of absolute pressure. There is 6 bars of absolute pressure, because devices measure gauge pressure. Okay. I can give you one more example. So blood pressure. Okay. All of you know that blood pressure should be in the normal range between 80 and 120 millimeter mercury scale. This one is the mercury. Okay, but this is not the absolute pressure, because so what is the atmospheric pressure? 1 atm is 760 millimeters of mercury scale. Okay, this is the atmospheric pressure, 760 mercury height. Okay. But your blood pressure is 80 and between 120. So it means that there is problem, because if it is the pressure of your body, then it means that this is somebody, I don't know his name. So inside him there is, so let's say 100 millimeters Hg, but environment is 760 millimeters Hg. Okay, so there is lots of pressure on it, lots of pressure, and this person will die. Therefore, there is some problem. The problem is that this one is not the absolute pressure. It is plus 760 millimeters Hg. That is the real pressure. Real pressure is, or absolute pressure is this one plus that one. Again, devices show the gauge pressure. So your heart produces more pressure than the atmospheric pressure. Otherwise, blood cannot flow. Okay? If the blood flows, it means that more atmospheric pressure, more than atmospheric pressure. Okay? That is the case. Or you can increase the number of cases. I can give you one more example so that you have football. Okay. Again, the pressure inside that ball is the gauge pressure, not the absolute pressure. So anyway, if it is not stated, you should know that the pressure measuring device measures gauge pressure instead of the absolute pressure. Any pressure measuring device measures gauge pressure instead of the absolute pressure. Okay, that is end for the first chapter. No, I have one more topic. Yes, pressure measuring devices. And with this one, we'll finish the first chapter and move on to second chapter. Okay? Second and third chapter together. So if you have questions, you can ask. We don't have